Okay. In this second part of the lecture, what I want to do is look at points of inflection and then the second derivative test. Points of inflection I kind of was just using on the last problem. I just didn't use that term. A point of inflection is a place where the concavity switches from concave up to concave down or vice versa. So just like we use the term critical points to describe places where the first derivative was 0, which meant the slope would go from positive to negative. Here we use the word point of inflection. You'll see it written as POI, and that is a place where the second derivative of a function is equal to 0, or if it's undefined. That's the point worth noting as well. So in these places where the second derivative is 0 or undefined, you often have the concavity of a function changing, again, from concave up, because it's concave up if the second derivative is positive, to down, or vice versa. So to find our points of inflection, it's really simple. We did it in the last problem when I found that second derivative and figured out where's the second derivative equal to 0. So that's what we do. So as an example, one of the functions they gave us is, I'm looking down at the book, f of x. This is a much shorter, easier one to take the derivative than last time. F of x is equal to x fourth minus 4x cubed. And so they asked me to find the points of inflection and the concavity for this function. Okay, so if I'm going to find my points of inflection, again, you always take the first derivative, then the second derivative. So first derivative is equal to 4x cubed minus 12x squared. And then if I take the second derivative, you can see how much simpler this is than the last one. This is 12x squared minus 24x. Now I want to know where is this 0. That's how I find those points of inflection. So I'll factor out a 12x. So we say 12x times x minus 2 is equal to 0. So we can see, looking at this function, that it will be 0 when x is either equal to 0 or 2. So those are my points of inflection, the places where the second derivative is 0. Now, if I wanted to kind of determine concavity, what I do is I take those points of inflection and I use them to make intervals. Again, just like in the previous section, we used critical points and found intervals out of that. Here I'm using points of inflection. So I can say, okay, one interval will be negative infinity up to 0. Another interval will be 0 up to 2. And then the last interval will be 2 up to, oops, I should write that, up to infinity. Okay, and so I choose a point in each interval. So here I'm going to say x is equal to negative 1. Here I'll say x is equal to 1. Here I will say x is equal to 3. And I plug this point in to the second derivative to figure out if it's less than, equal to, or greater than 0. So I take the second derivative at negative 1, second derivative at 1, second derivative at 3. And I just plug and chug these values into this function. And so when I do that, sorry, I'm kind of cheating to look at the numbers because I don't have a calculator down here. This one ends up being greater than 0. This one ends up being less than 0. This one ends up being greater than 0. So what does that mean? That means that if this is greater than 0, it's concave upward on this range. This would be concave downward. And this would be concave upward. Okay, so really, in this example, there's not much that's new, right, from what I was doing in the last lecture. We're just kind of giving a name to this term, defining these values, these points of inflection, but otherwise we do exactly as we were. So we can use those points of inflection, places where the second derivative is 0, to determine where we have intervals of concave up, so that means where our slope is increasing, and then where our slope is decreasing when we're concave down. The last concept, so this you do in really with the problems we were previously doing. To find your places where things are concave, you have to use points of inflection. The last kind of problem is the second derivative test, and those can be a little bit different. Okay, so second derivative test. Sorry, I'm looking for my eraser. Yeah, let me turn the page so I can write down my problem. Okay. The second derivative test kind of puts it all together. And you will have the, if you're following along with me in the PowerPoint, the formal language of it typed up there. But the second derivative test essentially says, if you actually look at a critical point, so if you look at places where the derivative is equal to 0. So if you look at a place where the derivative of a function is equal to 0, if at that place the second derivative is greater than 0, or the second derivative is less than 0, we can find our maximum and minimum. So if we have a place where the first derivative is 0 and the second derivative is less than 0, this is going to be actually, sorry I can't talk, a maximum value. And if we have a place where the first derivative is 0 and the second derivative is greater than 0, this would be a minimum value. So the example problem they give us is this. Let's see. We want to find the relative extrema for this function. F of x is equal to negative 3x to the 5th power plus 5x cubed. And we're going to use the second derivative test to find those. So, first, we take the first derivative, then we'll take the second derivative and find some of those important points. So the first derivative of this function is equal to negative 15 x to the 4th plus 15 x squared. And the second derivative of the function is equal to, what's 4 times 15? 60. Negative 60 x cubed plus 30x. Okay, so to use the second derivative test, first I'm going to go and find those, not points of inflection, I'm going to find those critical points, the places where the first derivative is 0. So where is negative 15x to the 4th plus 15x squared equal to 0? So clearly I can factor here a 15x squared, which leaves me with, I'm going to switch the order here, 1 minus x squared is equal to 0. And so this gives me critical points at x equals 0 and at x equals plus or minus 1, right? And so what I want to do at each of these 3 places, I want to find the second derivative. So I'm going to just plug and chug these values in. I want to know what's the second derivative. So I'm not making intervals out of this. What's the second derivative at negative 1? What's the second derivative at 0? What's the second derivative at positive 1? So I'm plugging those into this function right here. So the second derivative at negative 1, I'm going to cheat and look at the answer. I should be able to do this in my head, but I don't have a calculator and I'm Trey's tired. So the second derivative at negative 1 is greater than 0, is all they say. So it's some positive number. The second derivative of 0 is going to be 0. The second derivative at 0.1 actually gives us a negative number, so it's less than 0. Okay, so what does this mean? So these critical points are places where I can have maximum or minimum. At negative 1, my second derivative is greater than 0. That means I have a minimum. This is a relative minimum value. 0, I mean, that tells me nothing. So it has to be greater than 0 or less than 0. 0, I ignore it. My second derivative at 1 is less than 0, which means I have a maximum value here. So This is my min, this is my max. So to go through again, to use that second derivative test, you first take your first derivative of a function and find any critical points for that first derivative. Then you have your second derivative, you plug in those critical points to the second derivative, and if that second derivative is positive, that's where you have a minimum, because it's like if you think about, I don't know, a function. Here the slope is 0, and I actually am coming up, right? So I would have a second derivative that's greater than 0, which would indicate a minimum. So that's what that means. If my second derivative, when I plug in the critical point, is less than 0, that is where I have a maximum, because I'm starting to come back down. And that's it.